A very good afternoon to all of you. Myself Deepti Jain, lecturer in electrical engineering from GPC Khuni-Majra Mohali. I am here to present a lecture on protection schemes for bus bars and feeders. As we know, our power system consists of major equipments like generator, transformers, transmission lines, bus bars, motors, etc. So the protection of all these major equipments is very necessary. So in this topic we will cover the protection schemes for bus bars and feeders. So first of all, let us discuss what are the main zones of protection for these equipments, how we can differentiate all these protection zones for every component of the power system. So first is zones of protection. Now for the fault anyway within the zone, the protection system is responsible to isolate everything within the zone from the rest of the system, and this isolation is done by the circuit breaker. And for this zone of protection, it must isolate only the faulty equipment or section from the healthier section, so that the continuity of the supply can be maintained without any interruption. So let us differentiate the main zones of protection. First is the protection is provided necessary for generator, for transformer, for bus bar, for the transmission and distribution line, that are feeders, and last is at the motors. So in this way we can differentiate the different zones of protection. Now this is where there is a generator. Now this protection scheme is generator protection. The second is protection is necessary for the bus bar. So this is a bus bar protection. The next is this is a transmission line. So that is why we have named here line protection, that is a transmission line protection. Again there is a bus bar. So this is a bus bar protection. After that there is a load, motor load. So this is a motor protection, and here there is a generator. So this is again a generator protection. So in this way every equipment of the power system needs a protection. So in this way we can name every equipment as a protection, that is a generator protection, bus bar protection, transmission line protection, motor protection and bus bar protection. Now the characteristics of these zones of protection. Now these zones must be overlapped. Now circuit breaker are located in the overlap region, and for the fault anywhere in the zone, all the circuit breakers in that zone open to isolate the fault. Now under the overlap protection, the first is there is no any blind spot, that is a neighboring zones are overlapped to avoid the possibility of unprotected area. Means no any area should be left uncovered where there is no any protection. The second is use overlapping CT. Now in this isolation is done by the circuit breaker. So thus it must be inserted in such overlap region to identify the boundary of the protective zones. And this is an example of overlap protection. Now overlap accomplished by having two sets of instrument transformer and relays of each circuit breaker. Now see, this is a red box is a circuit breaker. Now these blue line and the black line shows the two CTs. Now this black line shows the CT for the zone 1, and the blue line shows the CT for the zone 2. Now there is a overlapping of these two zones. See, the left side is a zone 1 and right side is a zone 2. So this can be achieved by the arrangement of CT and circuit breaker. Now the overlapping can be done of the different zone by just placing the CTs and circuit breakers to a proper place. The next is, what is primary and backup protection? The primary protection is the protection provided by each zone to its element. However, some component of a zone protection scheme fail to operate, so for that we have a backup protection which is provided and take over only in the event when the primary protection fails. So we can say that protection is basically of two types. First is known as primary protection and second is known as backup protection. Now the primary protection is that protection which is provided by each zone to its element, and whenever this primary protection fails to operate, and in that case the backup protection is provided. Now let us consider an example. So consider the power system shown below with the generating source beyond buses 1, 3 and 4. Now there are 3 buses 1, 3 and 4. Now you know what are the zones of protection in which the system would be divided. Now we have to divide this power system network into different zones of protection, and the second question is, which circuit breaker will open for the faults at P1 and P2. So let us solve this question. So this is the power system network that is given to us. Now the fault is at P1. First, the zones of protections are, now this is the first zone of protection. Now fault at P1, now there are first 3 zones of protection. Now for this bus bar 1, for bus bar 3 and for this overlapping. So suppose the fault is at P1, then the circuit breaker will operate, that are A, B and C. So all the circuit breaker which are covered in this box will operate. Now second is fault at P2, then this fault is located in 2 zones, this zone and this zone. So all the circuit breakers in these 2 zones will operate to isolate the faulty section from the healthier section. So let us see what is the answer. Now for fault at P2, circuit breaker A, B, C, D and E will operate. The second example, if 3 circuit breakers are added at the tap point 2, now we have to add 3 circuit breakers at this tap point 2. How would the zones of protection be modified, and which circuit breaker will operate for fault at P1 and P2 under these conditions? Now here at P2 I have added a bus bar and 3 circuit breakers are added in this way. Now let us see different zones of protection. Now here we have this much zones of protection. Now again fault is at P1. Now for this only 2 circuit breaker will operate, and that is A and F. Now fault is at P2. Now for this we have to cover these 2 zones. So the circuit breaker G, C, D and E will operate. So we can discriminate each zone in this manner. A system as shown with relays and breakers are marked. A single fault has resulted in the operation of breaker B1, B2, B3 and B4. Identify the location of the fault. Now these breakers are operate because of the fault B1, B2, B3 and B4. So, for this the fault is somewhat at this point. So, fault in the overlap zone at breaker B2 as shown. So, for this we have two zones of protection. So, the fault is at B2. The next is backup protection. It is also known as duplicate primary protection. It provides primary protection when the primary relaying equipment is out of service for maintenance or repair. It disconnects when the primary relaying operates correctly. It operates with sufficient time delay if the primary protection fails to operate. Now, when the short circuit occurs, both primary and backup start to operate, but if the primary is operate, then the backup will reset. The second type for the backup protection is remote backup protection, and it is located outside boundary of the zones of protection, and it will operate when both the primary protection and primary backup protection fails to operate. Now, see again examples. Now, for this section station K, which one is the primary protection and which one is the backup protection? Now, see, for this station K, C, D and E will be the primary protection, and all the rest breakers A, B, F, G, H, I, J are the backup protection. The next is protection of bus bar. So, after the zone discrimination and the protections methods, that is the primary protection and backup protection. Now, let us begin with the protection of bus bars. Now, first of all, introduction. What is basically a bus bar? Bus bar form a link between the incoming and outgoing circuits at the generating stations or substation. Basically, bus bar is a kind of node through which the various connections can be made. So, if a fault develops in this part of the power system, considerable damage and disruption of the supply will occur. So, to reduce the effect of fault, various bus bar arrangements are employed. So, still proper protection scheme has to be adopted to improve the reliability of the supply. Although the various schemes have been developed for the protection of bus bars, but the most common protection scheme for the bus bar is differential protection scheme. So, this is the bus bar differential protection. So, see, this dark line shows the bus bar. Now, as I have told you, bus bar is a kind of node through which various connections can be made. So, see, this is the incoming feeder to this bus bar, and to this bus bar there are suppose two outgoing feeders. So, these are the circuit breakers that we have connected. Now, for the differential protection, what is the arrangement? We have connected CTs on the both side of the circuit breakers, that is on the incoming side and to the outgoing side, and their secondaries are connected in parallel. Now, between this secondary we have connected the operating coil, or you can say a relay coil, which will trip if there is any difference of the current, that is the incoming current and the outgoing current. So, see, differential protection scheme, the secondaries of all the CTs connected in incoming and outgoing feeders are connected in parallel as before. The CT is designed in such a way that under normal condition, the EMF induced in the secondary of the CTs placed on outgoing feeder. Then no current flows through the operating coil of the relay, which is connected across the connecting wire. So, operation under normal operating condition or external fault condition, the sum of the incoming current must be equals to the sum of outgoing current, that is KCL, Kirchhoff's current law. Therefore, no current flows through the operating coil. So, see first of all the arrangement. Now, under the normal condition or you can say if fault is outside this protection scheme, in this way the incoming current is equals to the outgoing current, means the same current will flow through these relay wires, Therefore, no current flows through the operating coil. However, when fault occurs within the protected zone or the bus bar, the current entering the bus bar will no longer be equal to those leaving it. Therefore, the operating coil of the relay gets energized, which will in turn closes the trip coil of the circuit breaker. Thus, a differential current flows through the operating coil of the relay, which closes the trip circuit. So, whenever there is a fault within this protection scheme, the incoming current will no longer becomes equal to the outgoing current according to KCL. So, that extra current will flow through these wires, through this operating coil of the relay. Now, which in turn operates the operating coil and gives signal to the circuit breaker. Now, why there is a requirement for the protection of bus bar? Now, first is high bus fault currents due to large number of circuit connected, that is which causes the CT saturation often becomes a problem as CTs may not be sufficiently rated for worst fault condition case. As we know, bus bar is a kind of node through which various connection can be made. So, for that there may be a number of CTs connected to that bus bar, and there may be a problem when that CTs do not have the same ratio. So, this will become a major problem. So, second is large dynamic forces associated with the bus fault require fast clearing time in order to reduce the equipment damage. Now, there may be a false trip by bus protection may create serious problems which will cause the service interruption to a large number of the circuits and system wide stability problems. So, with the both dependability and security, important preference is always given to the security. So, these are the some bus protection techniques: interlocking schemes, overcurrent, or you can say that unrestrained or unbiased differential scheme, overcurrent percent differential technique, linear coupler, high impedance bus differential scheme, and low impedance bus differential scheme. Now, this is the interlocking scheme. Now, this is here the blocking scheme is used, now in which the incoming CTs are interlocked with the CTs at the outgoing feeders. The short coordination time is required for this, and the care must be taken with the possible saturation of the feeder CTs. Now, here the main now these CTs must have same turn ratio. Now the blocking signal could be sent over the communication ports, and the technique is limited to simple one incomer distribution buses. The second is overcurrent unrestrained differential scheme. Now here the incoming and outgoing CTs are collected via a single differential signal formed by summation of all the current feeding bus. Now CT ratio matching may be required. On external faults, saturated CTs yield spurious differential current, and the time delay used to cope with CT saturation. The third category is linear couplers. Now these are the linear couplers whose secondaries are connected in series. Linear couplers are fast, secure. It required dedicated air gap CTs which may not be used for any other protection. It cannot be easily applied to reconfigurable buses. The scheme uses a simple voltage detector. It does not provide benefits of a microprocessor based relay. Now this is a high impedance differential scheme. Now next is feeder protection. The chances of faults occurring on the feeder is much more due to their great length and exposure to the atmospheric conditions. Therefore, various protection schemes have been developed which may be classified as time graded overcurrent protection, differential protection and distance protection. So this protection of lines must have some special features such as during the fault the only circuit breaker closest to the fault point should be tripped. If the circuit breaker closest the fault point fails to trip, then the circuit breaker just next to this breaker will trip as a backup. The operating time of the relay associated with the protection of the line should be as minimum as possible in order to prevent unnecessary tripping of the circuit breaker associated with other healthy parts of the power system. The first protection scheme is time graded overcurrent protection scheme for the bus bar. Now in time graded overcurrent protection scheme, the time setting of the relay is so graded that in the event of fault, the smallest possible section of the system is isolated. This scheme is applied for the protection of radial feeder, parallel feeder and ring main feeder. Now first is radial feeder. The time graded protection feeder is obtained by employing inverse definite minimum time lag relays. The relays are so set that the minimum time of operation decreases from the power station to the remote substation as shown in the figure. That is in the next slide. The operating time of the inverse definite minimum time lag relay is inversely proportional to the operating current, but is never less than the minimum definite for which is set. As we can conclude that more the fault current, less will be the operating time of the relay, and if the fault current is low, then the operating time may be high as compared to the previous case. Now, this is the example of, this is the time graded protection for the radial feeder. Now, this is the generating station, this is a transformer. Now, these are the different circuit breakers on the feeder. Now, see, we have set a proper tripping time for each circuit breaker, and this time decreases from this generating station to the source station, substation. So, this is 2.1, after that 1.6, 1.1, 0.6 and 0.1. Now, if a fault occurs between station E and F, now suppose the fault is between E and F substation, it will be cleared in 0.1 second, means for the fault in between E and F, this circuit breaker having a tripping time of 0.1 second must be operate, because all other relays have higher operating time. Now, if the relay at substation E fails to trip, then the relay at substation D will operate after a time delay of 0.5 seconds, that is after the 0.6 seconds from the occurrence of fault. Similarly, if D fails to operate, then the circuit breaker at C substation will operate at a 1.1 second from the occurrence of fault. The next is advantage of definite time line protection. Now, the main disadvantage of this scheme is simplicity. This is very simple arrangement. The second major advantage is during the fault, only the nearest circuit breaker towards the source from the fault point will operate to isolate the specific position of the line. Disadvantage: now if the number of sections of the line is quite large, the time second of the relay nearest to the source would be very long. So, during any fault nearer to the source will take much time to be isolated. So, this may cause severe destructive effect on the system. The next is time graded protection for the parallel feeders. Now, where continuity of the supply is absolutely necessary, two feeders are run in parallel. Now, if a fault occurs on one feeder, the supply can be maintained from the other feeder, disconnecting the faulty feeder. Following figure shows the system where two feeders are connected in parallel between the generating station and the substation. So, first of all, what is a parallel feeder? Parallel feeder is necessary whenever the continuity of the supply is very necessary. So, at the generating station, non-directional overcurrent relays are connected, whereas the directional overcurrent instantaneous relays are connected at substation end. So, let us see the diagram. So, this is the source substation and this is the receiving substation. Now, see, nearer to this sending substation we have a non-directional relay. Now, the relay having both side arrows, it means it can operate in either of the both sides. So, that is why it is known as non-directional relay. Now, to this receiving substation, here we have directional relay, means this relay will operate when the direction of the current will be in this direction. Now see, if the fault occur at this feeder 2, now what will happen? Now if an earth fault occurs on feeders at point F as shown in the figure, the fault is fed. The fault is fed by two ways.